Hello everyone. Let us look at some problems from analog CMOS design by Professor Behzad Razavi. So these problems are mainly to get some intuition in the circuit solutions. So instead of going much into the maths, let us try to do these problems intuitively. So let me start with problem 3.15a. I don't know what is this problem in the old book, but in the new book, I think it's 3.15a. But yeah, let me draw the circuit. So this is a common gate configuration. This is a bias voltage, and we have a vein here. So before doing anything, first let us do a quantitative analysis on this. So we know that we can find out VO by VI by using some logic or by using some small signal analysis. But that small signal analysis is true. Small signal is true only if the transistor, I'll just call it TX, is in saturation, right? But we want to find out V out versus VI, mainly large signal. So we need to understand the actual trend of V out versus VI, and we need to correctly visualize how the transistor M1 goes through its different regions of saturation, triode, subthreshold. So as V increases, how does it change the regions? So we need to understand that. Small signal analysis is anyways straightforward for this circuit, so we'll not go into that. So let us consider the case where Vi is 0. When Vi is 0, M1 gets the full VB minus 0, right? So with the case where VB is greater than VTH, we can say that if when Vi is 0, M1 is turned on, right? Right. So when we turn on the M1, VO may be so low that this M1 will go into triode, or VO may be quite high so that VO minus Vi is less than VB minus Vi minus VTH. So it's in saturation. So what will that depend on? So how can we say that VO is low or not? So that will mostly depend on the RF, right? So if RF is small, then we can say that when we turn on VB minus Vi, RF will draw in some more current, and thus V out will go down a little bit. So if RF is small enough, then when we turn on M1, it can turn on in triode region. And then as we keep on increasing Vi, the current drive of the transistor keeps on decreasing. So as the current of the transistor keeps on decreasing, the current sourced from VDD also keeps on decreasing. So V out will keep on increasing. So at some point, uh, M1 will go into saturation. and if VB minus VI is less than VTH for some VI, then it will turn off, right? So uh, let us consider that RF is small enough. So our transistor will start in triode region, then it will go to saturation as you keep on increasing the VI, and then it will cut off, right? So for the sake of making it a little more simpler, we'll start our analysis from the cutoff region. Okay, so what will be V out versus Vi when the transistor is no more there? So let us quickly draw the simple circuit when there is no transistor. So the transistor is off, that means it is not drawing any current, so we can just ignore it, right? So we have this RD, there is this transistor, and we have RF. Okay, so this is wrong. We have V in here, right? Transistor does not turn on, so we might as well, you know, do this. So in this case, our V out will simply be a voltage divider. So V out minus Vi equal to RF by RF plus RD VDD minus Vi, right? Vi, I'm considering Vi as a reference. So the full voltage is VDD minus Vi, that is here. A part of it is VO minus Vi, that is here. And what is that part? It's a voltage divider, RF by RO. RD plus RF. So we can just find it out from here. This will be equal to RF VDD will be in the numerator. Minus RF VI. So RF कट जाएगा plus RDVI, right? So this is how the graph will look when the transistor is no more or the transistor is not drawing any current. So let me just quickly plot this. I am working in the third region. This is a simple line with a slope equal to RD by RD plus RF, and with a y-axis uh, intercept of RF VDD by RF plus RD, correct? So we know, okay, so let me just demarcate VA, VB. So these are nothing but the values of V in, just to differentiate between the regions. This is V out. So after VB, the transistor is cut off. Between VA and VB, the transistor is in saturation, so that we can use the simple saturation region current equation to find out the curve here. So let us do that. Let us try to find out the voltage in the region B. So we know that transistor is in saturation, so we can use the small signal analysis to find out VO by VI. So that's a straightforward thing to do. But we want to understand how exactly do we reach the small signal, uh, you know, small signal gain, or how can we go to the small signal gain from our large signal analysis, right? So that is what we want to know right now. So to do this, we'll need to again redraw the circuit, but this time there will be a transistor here because it's on, and it throws out a current that depends on VI, and the dependence is square law, right? It's the saturation region current. So this is RF, we have VP, we have VI, we have VO, right? So how do we find this V out without going into too much trouble, right? So we can already see that there are three sources here. One is VDD, one is the VB, one is VI, right? Three. Okay, let me change the pen color. Three independent voltage sources and one dependent current source. So what is this dependent current source? This is nothing but the transistor. Okay, let's just forget about this dependent current source right now. We want to find out V out here. So let us use the short circuit current method to find out V out. So along with short circuit current, then we need to find out the R out also. Looking like this from here. So this is pretty straightforward. To find out R out, we just add a voltage here. We turn off all the independent voltage sources. So we turned off all the independent voltage sources. This is nothing but RD parallel RF. RD parallel RF. So we already have this straightforward number. What is ISC? So ISC will be a superposition of three different terms of uh, current. One comes when VDD is active and VB, VI are 0, right? If VB and VI are 0, and to find I short circuit, we have to short circuit the V out to ground. So if we do that, let me erase this. So this must be clear, how to find out R out. So that's straightforward. So I'll erase that. Let me keep this here. So to find I short circuit, we'll first turn off VBVI, keep VDD. So the current flowing uh, uh, out from this is nothing but VDD by RD, right? Now turn off VDD, turn off VB, keep VI on, right? So if we do this, if we turn off VB and just keep VI on, then uh, the current flowing here will be VI by RF. So this is VI by RF. Why? Because when we find out the component uh, at ISC due to VI, we make VB equal to 0, and for VB equal to 0, VI is always greater than 0, so transistor is off, so it's less than VTH. And in the case where Vi is 0, VDD is 0, there is only VB, we have minus ID. Okay, let me explain this a little bit more. For the third term where only VB is active, so the circuit will be like this: RD, there is ISC, so both of them are at 0, both of the potentials are 0, so there is no current through RD. Okay, so it is out of question. We just have RF here and our current source. So RF also goes to 0 because Vi is 0, so there is no current here. So ISC is just this current. ISC is just minus of this current going down. What is the minus of current going down? The downward current is ID. That's why I have written here minus. So taking all these into account, V out will be VDD by RT plus Vi by RF minus half mu n CMOS W by L VB minus Vi minus VTH whole square, large signal current, and multiplied by RD parallel RF. So this is a simple equation. Now if we want to find out gain, what is Vi out by Vi? So gain is actually, it's not absolute gain, is not absolute V out by Vi. V out and Vi are large signal values here. Gain is equal to small V out by small Vi, which we can also write as a small change in large V out by a small change in the large Vi, right? So this is the whole basis of small signal analysis. So to find that out, del V out by del Vi is VDD is the constant term, it will go to 0. We'll have a 1 by RF term, and we'll have a mu1 COX W by L VB minus Vi minus VTH, right? RD parallel RF. This is GM, right? GM is something that depends on Vi also. So GM is also non-linear. This is the linear term, linearized term, right? So our answer is GM plus 1 by RF times RD parallel RF. This must be a very similar result, right? This is a similar result. If we use a small signal analysis, we'll find out this number. But what is the basis for that number? So we have gone through this. Okay, this is a positive gain. That means if V in increases, V out will also increase along with that. So now let me draw the curve again. We have already drawn VB after VB. It's a linear curve. Between VA and VB, if we look at the V out with respect to V in here, it's a non-linear, some portion is linear, 1 by RF, some portion is non-linear, or a little bit of parabola. So there is no good way to draw it, but we can make, we can make it like this, right? I'll draw a better version after I complete the other part. So for between 0 and VA, current is in triode, and we can very well say that to maintain the continuity at position at VA, we can make it like this. The important thing to note here is that uh, V out at V in equal to 0 will not be 0. That's the most important thing. It will be some value, some del V, and it will depend on the value of RF in proportion to RD. If RF is small, then del V is small. If RF is large, then del V is obviously large. But yeah, this portion is triode. So in reality, I believe this will look something like this. So you start in triode, you have a steep curve in saturation, and then you have a linear curve when transistor is off. So this is how it will look like. So why did I make the curve steep here? Because it's a gain. It's the small signal gain. Small signal gain will usually be higher in saturation than in triode region. Okay, so this is how the curve will look like. So just for the sake of completeness, let us find out the small signal gain also. So when we talk about small signal, we just talk about this portion between VA and VB where M is in saturation. So that's the small signal portion, right? So for the sake of completeness, let us quickly find out the small signal gain. RD, RF, VI. This is ground, this is V out. So we'll arbitrarily assign the currents. At node V out, this is minus V out by RD equal to minus GM VI plus V out minus VI by RF, right? So this is 1 by RT plus 1 by RF V out equal to VI GM plus 1 by RF. It's a similar, you can already see the result here. So AV equal to this by this, right? So AV equal to GM plus 1 by RF by this term, and 1 by RD plus 1 by RF is nothing but RT parallel RF. Okay, so this is the answer, but let us look a little deep into the solution here. We have simply put a current, we've simply solved the current equation at this node and found out this number. But couldn't we also find out the current equation here at this node, right? So it's the same circuit. So wherever we choose to, we can solve the current equation, find out the results, right? So will it work here? Let us check. So at this node, the current equation is minus GMVI plus V out minus VI by RF equal to 0, right? So there is already a difference in the equation. So from this we get AV equal to V out by VI, right? So AV equal to RF times GM plus 1 by RF, correct? So what's going wrong here? Why is there a difference in the result? So the difference here is when we consider Vi to be the node voltage here, and we just write two currents at this node, we ignore the current going downward. Vi is a voltage source. It can draw some current, some finite current, right? We don't know what that current is. That is the sum of these two currents, but it will draw finite current, right? But by writing just these two currents, we are ignoring that finite current. So what does it mean when we ignore a current? It means that the impedance here is very high. So we are mainly looking at something like this. Suppose this R is very high. R is very high, and we are putting a Vi here. So at this node potential will still get Vi, but the current will be zero. So when we are using this equation, we are inherently assuming this. So when you do that, that means there is no current going downward. And if there is no current going downward, nothing will get sourced from upwards, right? So if this I is zero, then this I will also be zero. So V out will just be a term of GM and RF, right? So if you see anyone doing this and telling you that if you find out that you are finding out two different answers by putting the current equation at two different nodes, you know the reason now. At this node, you have to consider a finite I also if you want to solve this node. So let us do that correctly. Okay, one more thing. This is not a question of correct or incorrect. This is the question of what does it mean when you apply a node equation here with just two terms. It means this. If there are two terms, that means I going downward is zero. If I going downward is zero, that means I coming from upwards is also zero. If both are zero, then you simply have a circuit like this, and that is what you are getting here. To truly get the correct answer, you need to uh, run the current equation at this node where you have all the currents correctly defined coming downwards and then going from V out to down to Vi, right? But we can also do it from we can also find the similar solution, the same solution from uh, applying the current equation here. Let us try to do that. Okay, sorry for not changing the color here. So we know that if we apply our current equation and V out, then we get a correct answer because all the nodes, all the branch currents are correctly defined. Right? So we'll try to define the correct branch currents for this kind of circuit also, and we'll try to find out the V out by Vi. So for that we'll need to first explicitly define I. Right. So at this node voltage is Vi. So current I equals to minus Gm Vi plus Vo minus Vi by Rf plus Vo minus Vi by Rf, right? Also minus Vo by Rt to minus Gm Vi plus Vo minus Vi by Rf, right? So if these two are same, we can say I is minus Vo by Rd, and that was anyways very clear from the start. There is one node here, current is coming down. There is something going on here, we don't know. There is another node here, current is going down. This current will always be equal to this current. So this is just finding that out mathematically. So now if we just solve this equation, or we can solve this equation by putting I equal to minus V naught by RT, it's the same thing. We'll get our usual solution, which is Gm plus 1 by RF parallel RT. So this is another way of looking at the small signal analysis. And uh, again, here by this analysis, I have just shown you some sort of fallacy that we can be vulnerable to while solving these circuits. So we need to truly understand um, the conditions of applying KCLs and KVLs and all those ISCs and VOC. So we cannot blindly apply them at any nodes we want. We need to understand the conditions at which they are being applied, and then we'll get a proper number. Otherwise we'll debate with our friends maybe that you are getting this, I'm getting this, so you're wrong, I'm wrong, who is wrong, we don't know. So that's it for today. We'll continue the other problems in the next few lectures. Thank you.